Good morning. Let's wait for another minute. So I'm gonna discuss with you about our schedule for our term paper and the presentation and our final exam. All right. So this actually is the final exam week, right? All right. Okay, so let's get started. I think other students are coming on their way. All right. So I just checked the campus calendar for this quarter, the fall 2022, and this is the final week. I plan to put the final exam for this class on December 6th. I believe that is a Tuesday, right? So we're gonna use the regular class time to take the exam. For the term paper presentation, I think we can do that on the Thursday in the previous week, which is the December 1st. I think it's a Thursday. We're going to use the lecture time to allow each of you to present your term paper. Usually what we do is like for each student, you can present your paper. You need to prepare a PowerPoint presentation file. And if you like, you can send it to me before your presentation to let me review it. And I can give you some feedback. So for each student, I think usually we do is like you present about like 10 minutes or 15 minutes, followed by 5 minutes question and answer. So this is the requirement for the presentation. For the final exam, I'm gonna prepare a test for you. So the test will consist 2 parts. The first part is like the short answers. I'm gonna give you some like questions. You need to provide your own answers to each question. That part will be same to everybody. And the final exam will be an open book exam. You can use anything like the book, the lecture notes, and even you can search online if you want to find some informations. And the second part is for each of you, I'm going to give you 1 or 2 small projects. So for each one, each of you will have a different sets of data. You're gonna use some of my practice code to help analyze your data and complete the projects. All right. So this is the plan. Any questions here?
No.
Mm-hmm. Good. Thank you, Lloyd. All right, let's get started. Okay. All right, we're going to continue talking about the interval mapping, the QTL mapping, interval mapping for the ordinal traits or categorical traits. All right, so last time we very briefly mentioned the difference between the continuous traits and the categorical traits, right? For example, the eye color, different people have different type of eye color, but this phenotype is not easy for us to describe each of the phenotype using numbers, right? The numerical. That's why we for this kind of data we need to use a little bit different setting to analyze this data. this phenotype which fall into different categories. All right. So this is the model. The first model we're going to talk about, the probit regression model. All right. So here, the trick thing is like the important thing here is like we try to use a latent variable to help us find the association, the potential connection between the covariance and the phenotype, the categorical phenotypes. So here, the capital Y is the categorical phenotype of interest. For example, let's say let's use this example. So suppose this Y represented the smoking status, and so in the population there are two status, right? The one is like smoking, the 0 is the non-smoking. All right, this is the categorical phenotype, and we want to find the potential factors that determine whether people choose to smoke or not. So this covariant could be like some like fixed effect or some like random effect from the from some genes. So we put these factors in this regression model, and how can we find the association between these risk factors to this categorical phenotype? So usually it's very difficult to find a direct connection between this because of the discrete feature of this phenotype. So what we do is like we will use another variable called the latent variable to help us connect these risk factors to this phenotype. And this variable is actually on this latent variable cannot be seen, cannot be observed. So that's why we put a Y star here. So the Y star is a continuous variable. I hope you can see the difference here. So this is the phenotype we are interested in. This is not continuous. This is a categorical 1 or 0, smoking or non-smoking. However, we're going to use another continuous variable, which can be used in this regression model. So it's easy to see, right? In this regression model, we can find the association between these risk factors with this continuous latent variable. Then how can we link this latent variable to the terminal variable, the variable we are interested in? So this is the link. So suppose this continuous Y star, if this Y star is greater than a cutoff, let's say 0, then this individual will fall into the first category, smoking. So we're going to use this regression model to calculate this continuous Y star. And if this Y star is beyond some cutoff, let's say 0, then yeah, this determines the category of this individual, right? However, if some risk factors determine that this Y star is less than 0, less than the threshold, then which means like this individual will fall in the other category, a non-smoking group, something like this. Actually, the theorem behind this is very advanced. So I don't think I should discuss that because this is a little bit beyond the scope here. But I would like to use some like simple, straightforward example to show you how this model works here, right? So I'm going to use this graph to show this. All right. So this x-axis actually represent a sigma. Epsilon actually is a continuous variable, and this y represent the density, the probability here. Okay. So you can see the linkage here, right? So if we use 0 as a cutoff, then we can easily rewrite this epsilon and the linear combination of this risk of those risk factors. All right. Okay. Now, if this is a density function, we know the area under the curve will be equal to what? Will be equal to 1, right? The total probability will be equal to 1. Okay, so this is the point here. Okay, we try to use this continuous epsilon here to find a cutoff which can divide the total probability, which is 1, into 2 parts. So the left parts represent the probability that the individual belongs to the first category, for example, the smoking group. And of course, the area under the curve on the right-hand side will be the other half, the other part, right? These 2 parts will add up to 1. So we actually divided this total probability 1 into 2 parts. So the left is the probability that any individual belongs to the smoking category, and the right is the probability that y equals to 0, which means the probability that any individual falls into the non-smoking category. So this is how we use this latent variable model to help us link the risk factors with the terminal variable, the terminal phenotype, which is the categorical variable, through a continuous latent variable here. And this latent variable actually can be expressed using this linear regression model, right? Yeah, is that clear? And this actually, those equations here represent how we use the normal function, normal density function, through this probit regression to calculate the area under the curve for 2 categories here. All right. Okay, so the previous, this slide actually shows the example that we only have like 2 categories, right? So the smoking on the left and the non-smoking on the right-hand side. Okay, this is a very specific situation. In some cases, we're dealing with more than 2 categories. For example, the eye color, right? We have more than 2 eye colors. So how can we analyze the genetic factors that that are contributing to the eye colors? If that is the case, so we may have like more than 2 categories, right? So here, I'm going to give you an example. This is a more generalized situation. Suppose we have like this many categories from 1 to p+1 categories, and we have this many samples in this study. We have n. So this is p+1, the total number of disease classes, and each individual can fall into one of these p+1 categories, disease categories, right? And we use this capital Y random variable to show which category each individual belongs to. So if this one equals to 1 when this individual belongs to the case category, then you see 1. Otherwise, you put 0 for other type of for other categories here. All right, and we use the same function here. We still use the probit link function. So this is how we calculate the expectation for each category for each individual. And so this is how we calculate the variance covariance matrix for the Y variable. Remember, this is the categorical variables here. We're going to use a latent variable excuse me, it's too dry. I think, yeah, recently the Santa Ana wind yeah, has arrived here, and everybody feel dry air, right? The temperature is shooting up, and and the humidity is going down. So yeah, very uncomfortable, yeah, this season, and we need to watch out the fire, the forest fire as well. So that's very dangerous. That's one of the major threats to Californians. Another one is earthquake. Yeah. All right. Okay, so this is the generalized form if we have like more than 2 categories. So using this graph, so I can show you how we deal with more than 2 categories, right? If we have more than 2 categories, the same, we have the total probability equals to 1. So this is the total area under the curve, right? And by using this probit link function, we can truncate this total area into different categories. And the area under the curve in different region actually represent the probability for each category. So for example, this is the probability for the first category and the second one, and so on. And we see so this model actually, so the take-home message here for this model is like, we use this linear regression model, which consists the risk factors that we want to investigate, right? So this is, we try to link this regression model with this categorical phenotypes through a latent continuous variable. So, right, and this is the take-home message for this model. Yeah. Okay, and as I mentioned, this is how we calculate this model. So this is the expectation for the phenotype, the categorical phenotype, and we translate this into some like latent variables here, right? And we can easily calculate using our equations or formulas to calculate the variance of this categorical random variables. So once we have this, we can use the likelihood, log likelihood, and the first derivative and the second derivative. So we can estimate these parameters here, right? We have the linear model, we can estimate the parameters, and then we can test those parameters to see if they are different from 0 or not, right? So this is how we can test the linkage between any potential genes or genomic loci to see if they are relevant to the categorical phenotype or not, right? So this is the same strategy. So we have learned this game before. All right. So yeah, this is the detail, the information about how we model this. And here, remember, so we are dealing with the categorical phenotypes. So that's why this link function is this, the probit link function. We use the probability of the normal distribution here. So this is a very special case. So the general case is like this. This is the link function. If we are dealing with a continuous variable, so continuous variable, this link function actually is a very special case, which is the identity function. So identity function means they're identical. So this equals to this if we're dealing with the continuous random variable rather than this categorical random variable. Okay. Yeah, if I'm too fast, if you have some questions, just stop me. Yeah, ask me a question. All right, anytime. All right. So once we have the model, the same. So we have learned a lot about this kind of skills, right? So once we can construct the likelihood function, So the likelihood function will vary depending on what model you're going to use. For example, here we use the probit link function to write the likelihood function. Yeah, this is a special form for dealing with the categorical random variable. So this is different, right? Before we're talking about the continuous phenotypes, quantitative traits. So we use a different form of the likelihood function. But here, once we're dealing with the categorical random variable, we use the probit function. So we use a different way to write the likelihood function. Once you have the definitively defined the likelihood function, the rest of the steps are the same. So you just take the log likelihood function and you just do the first derivative and then the second derivative. You set the first derivative equal to 0 to solve the equation, right? Then you can get the estimation for the parameters of interest. And if you want to calculate the variance of the estimation of the parameter, you do the second derivative and get the information matrix, and then bingo, you're done. So if you have the estimation for your parameters, and if you have your variance of this estimation, then this is what we know, right? So you can form a wall test or F-test to test whether this is 0 or not, right? And this is how we test the association between any genomic loci and the phenotype. So no matter whether this phenotype is a continuous phenotype or a categorical phenotype, we use the same strategy, right? Okay, so for this model, we have two options here. So the simplest option is to treat the variance. Actually, the variance are equal across all the individuals. So if this is the case, so this is a similar case. So we're gonna assume the homogeneous variance. So this assumption actually make your model a little bit easier. All right. But if this is not the case, if your study sample, the individuals in your study sample, if they are, if they have very different scales of the variability, like a residual variance, probably the homogeneous variance model is not a fit, it's not an optimal, so you have to use heterogeneous like variance model to handle this variability. Okay, so this is how we use the heterogeneous variance model. Because for this one, this is a little bit complicated, because for each individual, you have to estimate the individual specific variance for that one, which means like you need more data, right? Because once you have more parameters to estimate, then you need to increase your sample size to compensate for the used degree of freedom. Yeah, that's the key point here. Yeah, for both model, we use the same weighted least square formula. So let's continue. And all right, and also we can use the mixture model method to help us analyze this data as well. So okay, so we have learned how we use the mixture model, right, to analyze the phenotype, which is a continuous variable. For example, still remember, so we're talking about the iris, the flower, the petal length and the petal width. So that's continuous. And So if we do not know the genotype, so we can use the EM algorithm, right? We treat the genotype data as a missing value. Then we can use the mixture model to do this. The same thing here. So instead of analyzing the continuous phenotypes, we can also use the same mixture model analysis to handle the categorical phenotypes here. The same thing, but we use a slightly different likelihood of function here. So this is the mixture. See, this is the probability that for each individual, what's the probability this individual belongs to each of the categories. So, and so we use the same setting for the mixture model analysis here, just very similar to what we used for analyzing the continuous phenotypic values. Okay. All right. Yeah, this is the mixture model, how we derive the variance of the estimation for the parameters here. So this parameter include the residual variance and the additive effects or the dominant effect. Excuse me. Okay. All right. All right. So this data can also can be also analyzed using the liability model. The liability model is very similar to the model I just talked about, the probit model. So here, liability model means like we use a different way to describe the likelihood function. Here we assume the residual variance is normally distributed. The liability model also use a continuous random variable, which is not observed in this data. So for example, this is the data we observed. So this is the data we observed. We observed in this study population, we observed the two categories. Either some individuals belong to the first category labeled by 0, or some of the individuals belong to the second category, which is labeled by 1. This is the observed data. Then we can use another y, the continuous random variable, which is latent variable. This one cannot be seen by the data sets, right? But we can assume there's an underlying y star that control this y here. So for example, this is the distribution of this y star, the latent continuous random variable, and this random variable actually is associated with the linear regression model here. So we can equate this linear model to this. And this, when we look at the distribution of this y star, the continuous one, it follows like this. So there's a cutoff. If this y star is less than this cutoff, okay, the individual with y star less than this value, this cutoff will belong to the first category. Otherwise, if the y star calculated for any individual is greater than this cutoff, is this area, then those individuals will belong to the second category. So the same thing, right? So we try to link the risk factors or the potential genetic factors with the terminal phenotypes, which is the categorical phenotype, through this latent variable. So this is the latent distribution, and we use this distribution to help us link this to this. The same. All right, so when we have like more than 2 categories, the same, right? So we just truncate this total area under the curve 1 into 3 regions. So this area actually represents the first category, the second category, and the third category, the same. Yeah, the liability model is very similar to the profit model I just showed you. The only difference is like how so what model we use to describe the likelihood function. Okay. So for the liability model, because there's a missing value, right? So which one is the missing? Can anyone tell me? Because here we want to use the EM algorithm. EM algorithm, I may give you a question in the final exam. So let me know when you should use, you can use a EM algorithm. So the answer is like, yeah, if you have a model, and in this model, if you are, if some like missing variables are involved, if you still want to use a simple maximum likelihood estimation model, then you can use the EM algorithm, right? So can anyone tell me in this situation, what is missing? So what is missing here? We have this and this, right? And we have, so this is Y. And we have the genomic data, which is this, the regression model. And the key point here is like we try to find the association. We try to link this. Oops. We try to link. Where is it? Oops. We try to link this with this, right? But it's difficult to directly link the genomic information with the categorical phenotypes. So then we try to leverage some like latent variables here to find the association. So first we try to link the genomic information with this Y star, and then we use the Y star to link with the Y, which is the observed categorical phenotype, right? This guy is missing. So that's the missing variable. Since we are dealing with a missing variable, so the EM algorithm will be a very good choice for us. Okay. So this is how we use the EM algorithm here. So it's the same. Once we have, so suppose there's no missing. So everything can be observed. Then it's easy for us to write the least square solution, right? Least square solution or the MLE solution. However, if something is missing, so for example, if Z is missing, Z is the genotypic value. So what we can do with the EM algorithm is what? Is we can replace this missing value by its expectation. We know how to calculate the expectation, right? The expectation for any random variable. We do not know the exact value for this X, but we can calculate the expectation for this guy. So this is how we calculate this. Right? Once we have this expectation, we just replace this expected value. We just use this expected value to replace the missing value here, right? This is Z. All right. Of course, they're different. They're different. The expected value for Z is different from the Z, right? The Z variable is actually the realized value for this random variable. But this one, the realized value is missing. We do not know, for example, for this individual, what is the genotype for this marker? We don't know, right? So we do not know the realized value for this marker. However, we can calculate the expected genotype value for this marker given the flanking marker information. Is that correct? Yeah, so this is how we can do. So if the marker is missing, we can replace the marker, the realized value of this marker by its expectation. So that's the perfect feature for EM algorithm. The same thing, if the Y is also missing, right? Because here so we only see the categorical phenotypic value, but we do not observe this continuous latent variable. But it's okay. So since it is missing, what we can do is like we can calculate the expected value for this guy, right? That's what we can do. And we can replace this guy by its expectation. Then we can easily write a code to implement this EM algorithm. So in each step, we just replace this missing value by its expectation. And after the each step is done, so we can treat this as a observed value. So the full model, no missing value. Then we can use the very close, simplified solution to get the MLE for each parameters. Does that make sense? Okay, very good.
I have a question.
Yeah, go ahead.
So do we have to do this like permute it like a couple hundred or 1,000 times to get any idea of where our response would be?
Yes, you have to do this by yourself in the final exam. Yeah, I'm kidding. This is too complicated.
I'm like, what?
Yeah. So this part is too far. I mean, so it's very hard. So I think if I give you a projector, so probably it takes you, even for me, it takes me like about like several days to. So it's easy to draft the first initial code, but the most time-consuming step is like you need to find some bugs, debug, right? So usually for the first round, but it's okay. So don't worry. In the final, I'm not gonna ask you to write any code by yourself. You just need to use my code. I will provide a lot of code. I have already provided a lot of code, right?
Yes.
One is the EM algorithm. So you can review that part as well. So that part, you run the EM algorithm with your data, and after the EM algorithm is converged, so the program will automatically print out how many iterations have been done, and what is the final estimation for the parameters at the converging step. So
so the program like R would stop at a certain point and tell you okay.
That's right.
I see.
So for example, in that code, the code I have already provided. So first we're gonna get set up a set of like initial values for your parameters. Let's say we have B0 equals to something. The initial value doesn't matter. You just randomly, arbitrarily give some values to this parameters, like let's say 0.8 or 1. Okay, now the program will do the EM algorithm, iterative algorithm. The first one, the second one step. So in each step, they're gonna check the convergency, whether the convergency criteria has been met or not, right? So for example, when the iteration goes to like maybe 38 times, yeah, at this point, the program will check the convergence criteria. If the convergence criteria is met, then the program will stop, and it will print out the solution for this and this. This will be the accurate estimation for your parameters. Yeah.
Right. Thank you. Thank you.
Yeah,
that was helpful. Yeah.
Yeah. So in the future, if you want to analyze your own data to answer some scientific question, probably you have to write your own code to do that. But yeah, so then
that sort of was my question. And
yes.
I'm thinking,
okay.
I see.
So in the future, when you write your own code, if you have question or problem, let me know so we can discuss that.
Will do.
Okay. All right, so this is how the EM algorithm can help us analyze this categorical phenotype data using this liability model missing value here, right? Okay. All right. So so just follow this. So when you write your own code for the EM algorithm to solve this problem, you just follow these steps to write your code. So it's easy for me, but maybe it's not that easy for you for now. In the future, if you practice more, so you will feel, yeah, this is not that hard. Okay. Okay. Yeah, the same thing. I mean, so the mixture model, and oops. So yeah, this is like example to show like two categories, right? For the phenotype of interest. So, and this is how we calculate the information matrix by using the second derivative. Yeah, very similar to what we have learned before. Yeah. Okay. The third way the third approach that we can use to analyze this categorical phenotype is through this logistic regression. So this is another way. Similar, very similar, but using a different way to express the relationship between this risk factors. See, this is the linear model, right? We always see the linear model, but in different way. So this is the linear model. We try to use this link function to describe the relationship between these risk factors with the y variable here. So where's y? So y is here. So we try to link this with this, and this is how we link this missing variable with the y here. The same. So I don't want to spend too much time on this part, but basically, yeah, this is the logic link function, and we can also translate this into the area under the curve. So if there's two categories, the left represents the probability for the first category, and the right represented the probability on the second category. They're actually the same, very similar to each other. The only difference is like how you use different model to write a different likelihood function. So yeah, after you successfully derive your likelihood function, the rest of the steps are the same. Just do the log likelihood, the first derivative and the second derivative, or you can use the EM algorithm, right?
Okay. Gia, I've never seen that symbol before in my life.
Which one?
That one, yeah.
I don't know how to pronounce this. So for this one, it's easy. Epsilon so I really sigma. No, that's not sigma. So yeah,
does anyone else know? Does anyone know in here?
I think it's zeta.
Zeta. Thank you. Yeah. I think it's zeta. I'm tired. I don't know. Like I'm not very good at like recognizing the letters or names. So, for example, if new people is introduced to me, so for the first time, I can never memorize this person's name, but I can immediately recognize this person's face. Next time when I see this person again, I know this person, but it's difficult for me to remember the name of the person. But after several times, yeah, this is why. So even I saw this letter a lot of time, but usually I don't know how to pronounce them. It's terrible. All right.
I think in our mind, we just say, okay, it's a variable.
That's smart. Yeah. In the future, when you become a professor, do this. Yeah, this is a new variable. Yeah. Don't ask me the name of this one, just a variable. Zeta. All right, thank you. Yeah. Thank you, Ryan. Yeah. Yeah, yeah, this is zeta. Yeah. Okay. I think I'm done with this. So this is just an example showing. So we actually use the same strategy to do the genomic scanning, right? So we can scan the entire genome. For example, this looks like a pomegranate genome. It's about the 360 St. Morgan. All right. So if we have the genomic markers, so we can test each potential genomic loci to see if they are relevant to the phenotype of interest. So here we're talking about the categorical, right? So we use the same thing. So you see the Manhattan plot, right? This is the genome, and this is the loss score, and we will specify a cutoff here. And once you see any signal go beyond this cutoff, that's an indication that within this genomic region there might be some like genes that are responsible for the variability of this categorical phenotype. And so as a statistician, so you can help your client or your research collaborators to analyze their data to find this region, and they can zoom in, they can look into this region to identify the real causal genes for the trait of interest. So, all right. All right, so I think I'm done with this chapter. So any questions before I move on? Okay, very good. Okay, let's continue. So, yeah, as you can see, right now my pace is very fast. Yeah. Okay. All right, chapter 11. So Mariano, so you missed the first part. So we were talking about the schedule for our final exam and the term paper presentation. All right. So I think the final exam, the final week will be the December 3rd to 9th, right? And so we plan to have our final exam on Tuesday, which is the December 6th. We're gonna use our class time to complete the final exam, and there are two parts in the final exam. The first part will be the same to everybody. I'm gonna give you the identical like short answer questions. I'll give you some questions, so you provide your own answer to those questions. The second part is for each of you, I'm gonna give you one or two small projects. I provide like different data sets for each of you. You need to use some of my practice R code to help analyze your data and get to a conclusion. Yeah. That's for the final exam. The term paper presentation will be on Thursday, December 1st. That's the 1 week before the final week. And so for each of you, of course, you're gonna spend some time to study your paper, right? Chosen paper. And you need to prepare a presentation file. And you have like 10 to 15 minutes to present your topic, and allowing for a 5 minutes discussion, the question and answer session. Yeah, that's all.
Thank you.
All right. Sure. All right. Next chapter is mapping segregation distortion loci. So this is a little bit different, but to me, it's the same. We just treat this segregation distortion as a phenotype, and we try to find the loci that are responsible for this kind of like a segregation distortion. So biologically, they're different. The purpose is different, but statistically, mathematically, they're the same. Yeah, that's why. So once you have you feel comfortable with the model we have learned in the previous lecture, you can do a lot of things in different ways. Yeah, we're learning tools, and you can apply these tools in many places. Okay. All right. So this is the classical, the standard Mendelian segregation ratio among different populations, right? We have learned F2 and backcross. So the F2 population, if nothing happened, if there's no other like genetic or evolutionary force for each loci, if this is F2, I mean F2 population, you're gonna see this 1:2:1 ratio, right? Magic ratio. Yeah, that's the standard classical Mendelian segregation ratio. For the backcross design, yeah, 1:1, right? And we have learned that the four-way is 1:1:1:1. And in this chapter and the next chapter, we're gonna talk about the segregation pattern in other populations. For example, the real population, the doubled haploid population, or the Heidelberg population. So if there's no evolutionary forces or other genetic forces, you're going to see this classical ratio here. However, this chapter, we're going to talk about different situations. So this slide actually shows you the definition of two other populations. The real population, the real means the recombinant inbred line. So this is one way we can breed some pure lines, right? If you have some like background in breeding, the plant breeding or plant breeding, so you know how we can get this real population. So for example, if we have like two pure parents, pure line, so this is the parental type, right? And so if we cross this two, we're going to get F1, which is the heterozygous. And if everything is different in terms of the genotype of each marker, so the heterozygosity coefficient will be 1 here. Okay, now if we do the selfing or we cross between the F1 individuals, we're going to get F2. So this is a typical F2 we can get, right? You see different heterozygous individuals here. Why? Because of the random crossover, right? So recombination. So in the F2, you're going to see many different genotypes here. All right. And if we keep crossing between each generation, so eventually, like after like maybe several generations, like 7 or 8 generations, you're gonna see each line will be purified. So this is due to the recombination, random recombination. And for each line here, the heterozygosity coefficient is less than the heterozygosity rate is usually less than 2%. So we can treat this as homozygous. So by doing this, you have to do this multiple times, multiple generations, right? Usually like 7 or 8 generations, you can get pure lines. And those pure lines, of course, they're different between each other, are called the real population. All right. So this diagram actually shows, yeah, so we start from 2 parental type, and we got the F1, which is the heterozygous. And if we go through the real population, so we just do like several generations, you're gonna get the inbred line, right? This is the real. However, this process can be done in a different way. So if instead of doing the generation crossing, so we just start from the F1. The F1, if the F1 produce gametes, so the gametes can be this, right? And we just double the genome for this gametes to produce the diploid individual. Think about this. This is one DH, the doubled haploid individual. You can generate another one, right? So with different genetic content. If you double this haploid gametes, you can get a diploid individual. So this is how we produce a pure lines population using this doubled haploid breeding. So we're going to talk about this again next chapter. So here we focus on F2 population. And then we want to see if there is some selection, the evolutionary force on this population. So what will be the segregation distortion, and how can we find the segregation distortion loci along the genome? So this is why we want to learn this in this chapter. Okay, so if there's no segregation distortion, if every loci is neutral, if there's no selection force or evolutionary force, what you see is like along this genome. So this is the genome. Along the genome, for each loci, you're going to roughly see the 25%, right? For one genotype, another 25%. Oops. So this is for the A1, and this is for the A2, and then you're going to see roughly like 50% of the genotype is the heterozygous, right? So you're going to see this ratio, this 1:2:1 ratio along the genome. So if there's no segregation distortion, so roughly the same. Okay, compared to this one, so what happened to this one? So you see difference, right? So you see, like, if you see pattern like this, for some region, yeah, they're okay. They are still following the classical, like 1:2:1 ratio. But for some region here, so definitely this is the deviation from the standard 1:2:1 ratio, right? And this region actually represent the region showing the segregation distortion, which means this loci, this genotypes probably under some pressure, some like selection force. All right, so this is what we want to analyze this time. So if we see this, we want to make sure this data shows a real distortion. So because for example, in this region, it's a little bit deviation from the 1:2:1 ratio, right? So how significant this loci is different from the 1:2:1 ratio. So this is what we can test. So we can test if this loci is under the selection pressure. Very likely this one is not, but this one is very likely to be selected, right, against or favored. Okay, so this is what we want to learn this time in this chapter. All right, suppose we have 3 linked loci A, B, and C. So we can, at each locus, we can examine the genotype frequency in this population, right? So for example, we use the pi represent the genotype proportion at locus A for this genotype. And yeah, this is what we can get from the data. And if this is the real data, what do you see here? Seems like B is under the selection, right? And this B1, the first homozygous genotype is being selected against, right? And this genotype is in favor. So that's why after the F1 population, you're going to see this genotype is overrepresented in the population, right? But this one is underrepresented. And why you see the same pattern but not that severe on the loci A and C? Why? Because they are linked, right? Even the selection is performed on B locus only, but because A and C are linked with B, so you're gonna see slightly biased genotype, frequency at these two locus. So this is why when you see this, for example, if you see, for example, the selection probably is acting on this loci, right? But you also see some like segregation distortion on the loci around this locus, right? Because of the linkage here. Yeah. All right. And let me see the time. Let me finish these slides here. Then we can stop and I can answer any of your questions here. Okay, so we can use this problem. How to pronounce it?
Probabilistic.
Yeah, thank you. Okay, so we can use this model to help us we can use this model to help us model the selection force here. So we have three locus here, M, N, and G. All right, suppose G is the locus being tested. All right, and you are familiar with this model, right? So we're talking about when we talk about the three loci analysis, we use this transition probability matrix, right? So given this genotype, what is the genotype for this marker and this marker? So the flanking markers. So this is the transition matrix. We use transition matrix again here to model this situation. Okay. Do you still remember this? Does this look familiar with you? All right, the transition matrix, right? Yeah. And I think for the three loci analysis, 3-point analysis, I gave you some practice R code. Yeah, you can use the similar transition matrix for analyzing this kind of data as well, the segregation distortion loci. All right, the same here. So given this locus takes this genotype, what is the probability that the two flanking loci taking these two genotypes here? So the same thing. And with this, you can easily calculate the likelihood function, right, under the Mendelian segregation. So the NAM model is, if the NAM model actually is associated with the NAM hypothesis, which means this locus is a neutral one. This locus is not, this locus doesn't undergo the segregation distortion, which means this locus is not under any selection pressure. That's the NAM hypothesis. However, the alternative hypothesis is, all right, this locus is actually under some selection pressure, and it will show some different ratio than this ratio. This is the classical ratio, right? If there's no selection, you're going to see this ratio. However, if there is some selection pressure, you're going to see a ratio which is different from this ratio, right? So that means like we have two hypotheses here. So this is the NAM hypothesis, and this is the alternative hypothesis. You can calculate the likelihood for both. So this is the likelihood for the NAM model, and this is the likelihood for the alternative model, right? Then you can use what? The likelihood function. Do you still remember? Yeah. something like this. Sorry. Something like this to do the test. And this can help you answer whether this locus, the G here, is under pressure or not. Right. Any questions here? Okay, then since there's a missing value, because sometimes like the G, for example, if we have the genotype data for M and N, but if we want to test some some locus in between, but this one, the genotype information is missing, so we can use the marker information on these two flanking loci to infer the possible genotypes for G, right? But this is missing. Then we can use EM algorithm to help us to do the calculation. All right, I'm gonna stop here today. So any questions? Any questions for the schedule for the of the final exam or presentation? Or so I think we still have like about 10 minutes. So if you want to discuss your potential paper, the term paper, yeah, we can talk about this now if you want. Yeah. Otherwise, yeah, we're gonna stop here.
I guess the only question that I would have is that aside from talking about the actual term paper, you said since it's mainly about statistics, how much do we want to focus on the statistics side of the term paper when making, the presentation or writing the paper?
Yeah, that's a good question. So usually for 10 minutes presentation, you don't have much time to describe everything, right? So the best way for this presentation is like maybe you take like you spend like first 1 to 2 minutes to describe the whole project. So that's not very specific for the statistic part, right? You just tell us about what is the purpose for this research. For example, if this research want to identify the genomic loci that are responsible for the yield of pomegranate or something like that. So the introduction for this paper, yeah, that's the first 2 minutes. But for the rest of the 8 minutes, or if you want a little bit more, like maybe 15 minutes presentation, then you can use the rest of the 12 or 13 minutes to just focus on the statistic part. So that's the 100%. Because for a paper, there's too many things to discuss, but we just want to focus on a specific statistical problem or question, a point you are interested in. Just take that part and focus on that. Yeah. For the rest of 8 minutes or 12 minutes.
Thank you. I definitely would have gotten that wrong. I would have not spent enough time on the statistic part.
Sorry, could you say that again?
Oh, I said I thank you because I would have gotten that wrong. I wouldn't have spent enough time on the statistics part.
Yeah. So because this is the whole point. So I hope I can see that you can benefit from this class, because this class I mentioned a lot of like statistical parts, but I didn't go too deep because this is not the purpose for this class. This class is quite try to be a educational, like let you know what tools and what things are available for different kind of research. So and if you can link your paper with one of my class topic, that'd be great. And so don't worry about like so you can, because for within 10 minutes you cannot just like go too deep. You just show us like for example permutation. So how this group of like this research group they use the permutation or bootstrap to help them find the real significant loci that are responsible for the phenotypic variation. So, and you don't have to describe the details that how they perform this bootstrap, right? But just give us a like outline. So how they did in their practice. Yeah, that's good enough. Does that make sense?
Yes.
All right. And after your presentation, yeah, please send me your PowerPoint files. I'm gonna keep those as a record. All right. Any other questions for now? If not, then have a good weekend and see you next time.
Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye.